Pop quiz. 2 silver half cells. One uses different silver ion concentrations. The other uses identical ones. Which setup gives a positive cell voltage? 5 seconds. Go. The answer? The one that uses different silver ion concentrations. In this video, you'll learn what a concentration cell is, how concentration shifts affect voltage, and how to calculate it with the Nernst equation, plus quick examples and pitfalls to avoid. By definition, standard conditions mean solutions are 1 molar, gases are 1 bar, and the temperature is 25 degrees Celsius. Under these fixed conditions, the measured cell voltage is called the standard potential, E0. However, real lab conditions rarely match the standard, so as concentrations change, the actual cell voltage shifts as well. By Le Chatelier's principle, if you increase the concentration of a reactant, the reaction is pushed forward and the cell voltage tends to rise. If you increase the concentration of a product, the reaction is pulled back and the voltage drops. Now here's the special case we call a concentration cell. Both half cells use the same redox couple, just at different concentrations. Under standard conditions, the cell potential is 0. But with a concentration gradient, the potential becomes positive. So how does the cell respond? It naturally tries to balance those concentrations. Silver oxidizes on the side with the lower silver ion concentration, the anode, and plates out on the side with the higher concentration, the cathode. In short, electrons flow from the low concentration side to the high concentration side, driving the system toward equilibrium. Think of it like water flowing downhill. Just as water levels equalize, electron flow works to even out concentration differences. Curious how much you're remembering? Your personalized practice test, flashcard set, and study guide are all waiting for you. Just tap the link now and keep watching. Future you will thank you. Now that we've seen the concentration cell in action, let's connect it to the thermodynamics behind the scenes. We start with free energy, written as delta G equals delta G naught plus RT times the natural log of Q. Next, we substitute. Replace delta G with minus NF times E, and delta G naught with minus NF times E naught. Finally, divide both sides by negative NF. And we arrive at the Nernst equation. E equals E naught minus RT over NF times the natural log of Q. In practice, we often work at room temperature, about 25 degrees Celsius. Under those conditions, this simplifies to E equals E naught minus 0.05916 volts over N times log base 10 of Q. For a pure concentration cell, remember that E naught is 0. For example, take the half reaction. Silver ion plus electron gives silver solid, with N equal to 1. Then, E equals negative 0.05916 volts over 1 times log base 10 of the silver ion concentration at the cathode, divided by the silver ion concentration at the anode. Plugging in the numbers, the log base 10 of 0.1 over 1 equals negative 1. Multiply that by negative 0.05916, and you get plus 0.059 volts. It's small, but significant enough to drive electron flow. Now, here's a common pitfall to avoid. Many assume that using the same metal on both sides always gives 0 voltage. In reality, that's only true when the concentrations are equal. As soon as the concentrations differ, a driving force appears, and that difference creates a measurable voltage. Let's extend beyond concentration cells. Balance electrons. N equals 6. Set up the reaction quotient. Q equals the aluminum 3 plus concentration squared, divided by the manganese 2 plus concentration cubed. Insert values. 1.5 squared over 0.50 cubed equals 18. Finally, compute the potential. E equals 0.48 minus 0.05916 divided by 6 times log base 10 of 18. That gives about 0.47 volts, slightly less than E naught, as expected when products are in excess. Watch out for mistakes. First, don't forget to raise concentrations to their stoichiometric powers when building Q. Second, always double-check N, the number of electrons transferred in the balanced equation. Third, remember that the constant 0.05916 volts only works at 25 degrees Celsius. At other temperatures, the factor changes. And finally, at high ionic strengths, concentrations no longer equal activities, so corrections are needed. To recap, unequal concentrations in identical half cells create a voltage. Use the Nernst equation. At 25 degrees Celsius, the 0.05916 volt rule. And remember, electrons flow from the lower concentration side to the higher one until the system evens out. Ready to quiz yourself with the content covered in this video? Check out the link in the description where you'll find Quizlet content made just for you.